Last week, we started the topics for inheritance. Specifically, we talked about the two designs without using inheritance, and we criticized on the pros and cons with respect to the single choice principle and also the cohesion design principle. And then we also talked about syntactically how you can use the keyword precursor, analogous to the Java super keyword, to actually make use of the code inherited from the parent class, and then try to reuse them as much as possible. So that's basically the first aspect for inheritance that we would like to talk about. This week, we'll try to continue to dive further into the inheritance topics, especially from the typing point of view. Let's see what the learning objectives are for this week. So we've talked about these two already last week. So we continue to talk about static type and also polymorphism, dynamic type and also dynamic binding. And we talk about typecasting. Why do we need it? And also polymorphism and dynamic binding, especially in the context of routine arguments. That's how you can build polymorphic collections, and also routine return values. So all these are the fundamental concepts for understanding all the design patterns that we're going to talk about starting from next week. Okay, and also generics. So we're going to review generics from a different perspective. Let's now review very quickly about the code reuse aspects for the inheritance, so we can bring you back to the context for the example that we have been using. First of all, click on the index over here, and then we want to go to, okay, let's see over here. Go to using inheritance for code reuse. Go to this slide here. Okay, so that'll be slide 18. You will see this slide, we have gone through them already last week. So what I will do is I'm just going to summarize them quickly on my iPad, so you will be up to speed and also brush up your memory about what the details are for this running example. Okay, so we basically got this inheritance hierarchy over here. So we got three classes. We got students being the parent class, and we got two subclasses. We got resident students and we got non-resident students. Here in the superclass students, we got two attributes. We got name for the students, and also we got a linked list of courses for the students. And these two attributes will be inherited verbatim into the subclasses. So let's just make a note over here. So these two attributes over here, they will be actually inherited to both here and also here, inherited. Okay, what about the routines? So we got two routines over here. We got register, also we got tuition, but they are treated slightly differently. Think about the register over here. The register, let's say both kinds of student will be registered in the same way. So that means similar to the two attributes we just talked about. So this will be also inherited verbatim to resident students. It will also be inherited verbatim to the non-resident students, also inherited. And then before I talk about the tuition, let's talk about why we should really consider its redefinition in the two subclasses. It is because in the two subclasses, for example, resident students over here, we have a new attributes called premium rates. So every time you're creating a subclass, the most common thing you will do is by introducing new data values, like a new attributes. In the case of the non-resident students, we are also introducing a new attributes called discount rate. And because we got new attributes, it also makes sense to actually got new routines. In this case, we got set premium rates for resident students, and also we got set discount rate for the non-resident students. You can think about these two attributes in this particular class is completely independent of these two attributes in another class. Think about these two classes, they're simply siblings. And in the inheritance hierarchy, siblings usually have nothing to do with each other. It's just that they have a common parent class over here. Of course, they inherit the common set of attributes or routines from their common parents. Finally, let's talk about the tuition. And for the tuition, it's really something that will get to be a little bit trickier later on when we talk about dynamic binding. Because you can see we got several versions for the tuition. Let me just highlight it properly. Okay, let's use pink. You can see the tuition over here at the parent level. Remember that one only calculate the base rate for just summing up all the fees for all the courses in the registration list. And then, so now in the case of the resident students, in that case, we're going to redefine. You can remember from the diagram lecture, plus plus simply means redefine. Okay, just remind you very quickly. So plus plus over here means redefine. And we also got redefine over here as well for the tuition for the non-resident students class. So now the reason we have to redefine for the tuition is because in this tuition over here, this you can think about, okay, think about the tuition over here is version number 1, which only calculate the base rate simply by summing up all the fees. On the other hand, the tuition over here is like a version 2. So this one will be the base rates will be applied by the premium rates, let's say PR. And symmetrically, this tuition over here is also redefined. And the way we redefine that is by declaring just by saying redefine, and then that'll be version number 3. So that would be the base rate calculation that's actually inherited from the parents over here, but by using precursor keyword, as we said last time. And then it'll be multiplied by the discount rate over here, multiplied by discount rate. So think about, we got 3 versions over here. We got version number 1, we got version number 2, and we got version number 3. At the runtime, which version that we want to invoke will be up to our need, but you have to be careful what you're doing. Otherwise, the dynamic binding may not be behaving like what you expect. So that's something we'll talk about later in the lecture. Okay, so that's a very quick walkthrough of all the routines and attributes that you have to pay attention to for this running example. Later in the lecture, we'll introduce another running example using a slightly more complicated inheritance hierarchy using smartphone. That's something we'll get into later. Okay, so let's now go back to the slides. So we have just reviewed about how the code reuse can happen using inheritance. So let's now move on. And we also talk about this particular test case about testing the object creations when we actually got inheritance. So that's something you can review from last week. And let's talk about something new, okay, for this week. So we want to distinguish between static type versus dynamic type. Let's see their definition. It's actually very straightforward, but we have to stick to the principle because things might get easily lost if you actually talk about deeper aspects for the inheritance. So in object orientation, which is what we're doing for design, an entity or variable has 2 kinds of types. So static type, so to be more precise, we talk about reference type, let's say specifically, just to make things simple. So a static type is declared at a compile time, which means whatever you declare the variable type to be, it's going to be unchangeable. Okay, it always stay the same. An entity static type determines what features it may be called upon. So basically, once I declare my static type to be students, versus if I declare my variable to be of type resident students, the consequence will be different. That's something we'll talk about, right? So this line here is very important for you to know, okay? And this applies to all the old object-oriented programming language you might actually use, okay? Not just unique to iPhone. Okay, what about dynamic type? Dynamic type literally simply means it's dynamic, which means it's changeable at the runtime. Especially, it would be very difficult to keep track of the dynamic type for your program. To be more general, it's an undecidable problem. Okay, that's something we'll talk about a little bit more when we get to the typecasting motivation. Okay, so now let's review quickly about the syntax between Java versus iPhone. The concepts are completely identical. It's just that the syntax have to be reviewed quickly. Okay, we also talk about this in your Lab 0 tutorial video, but I just want to make sure you really get it. Okay, let's take a look for syntactically how we distinguish between static versus dynamic types. Let's talk about Java. Okay, in your previous OOP course. In the case of Java, so let's say this. Every time you want to declare some variable over here, for example, S versus RS, you will put the type over here to the left of the variable. So you can think about these two on the left-hand side are simply the static type. And once S and RS are declared to be of student type, you cannot change it. Okay. On the other hand, if you look at on the right-hand side, you can see, first of all, you have the new keyword. The new keyword tells you that you're creating new objects. That's something you know very well. And then, after the new object, you're saying at that point of execution, you want to assign an object dynamically of type students versus resident students to either S or RS, respectively. So we called student and resident student over here the dynamic type. And as you know in Java very well, so if I say S, let's say for example, if I say students, S is assigned to maybe some new, for example, RS, resident students. I can easily do later to say reassign S to be some other types. So that means dynamic type, for example, NRS, non-resident students. So that really means you can definitely change the dynamic type as often as you like, as long as your application needs that. Okay, so that's about Java, how you can tell between static versus dynamic type. What about in IFO? In this case, in some ways it's easier to tell because we definitely distinguish between declaration versus usage for your variable. So let's take a look. You can see here, whenever you have a local variable declaration, or simply at a class level, you're simply declaring some attributes similar. Let's say for local variable declaration. Here you can see S and RS. At the runtime, we are saying that it's going to be a member of students and student over here, right? So this is the declaration. So these are the static type. What about dynamic type? For dynamic type, so whenever you're trying to use a creates, so these are analogous to the new keyword in Java. So these are for creating new objects. And right beside the creates, you're going to put under curly brackets over here. So whatever type you put over there, you're saying at that point of execution, you would like to assign objects of that particular dynamic type to the variable. Store its address into the variable. So this will be dynamic type. Okay, so this is something you're supposed to know already from Lab 0. I'm just trying to brush up the concept together with you. Okay, one more thing. This is simplification you can do in IFO. So let's say this. If I declare S to be of static type students, and then if it happens that the dynamic type will just be the same as the static type, in that case, you don't have to put any curly brackets over here. So writing this without the curly brackets is as if you actually wrote the following. You wrote creates, and then you simply put students. And then as the make Alan. So these two are completely equivalent. You can think about this one over here is more like a syntactic shortcut to this one over here. For this one here, you're just saying the student's dynamic type is just the same as a static type over here, but you got to distinguish between them to really know they're different. So the students over here, let me use a different color. So the students over here is the dynamic type, which just happen to be the same as the static type, which is common. Okay, so that's about the syntax between static versus dynamic. So let's now move on to an exercise for you. Okay, I do have a handout for you for this exercise. If you simply go to the lectures page and download this PDF, and let me just walk you through what you're supposed to do for this exercise yourself before you go on with the video. So part one, you have to look at this particular inheritance hierarchy that we just reviewed for the students, resident students and non-resident students. And then, so here, the title over here is really important. Static type declares expectation. Expectation is like what clients are supposed to or are expected to call on a variable declared to be of some particular static type. For example, if you see S1, S2, S3 over here, they are of the same static type students. RS is of another static type, and the NRS is of another static type. You will see my color convention throughout the lecture will be, whenever I talk about static type, I will typically use green. And whenever I talk about dynamic type, I'll use red to denote the runtime phenomenon. You can see once we declare S1, S2, S3, RS and NRS to be of the various static types. So now let's say we try to assign them or attach them dynamically to different types of objects. For example, you can see for S1, we simply attach dynamically a student object to it. Okay, and then similarly for S2, S3, and etc. Okay, so now your exercise is to really fill in this matrix over here with many empty cells. For each empty cell, you're going to put either a check or a cross. When you put a check, that simply means, for example, if I say, so here you can see S1 dot. We're trying to use a dot notation, which is very fundamental for OOP. So if I say s1.name over here, should I compile? I'm only talking about compilation. So in some way, expectation that we are talking about is really a compile time expectation. So that's something we want you to get some intuition and really get that principle into your mind before we go on with the lecture. Okay. So now if I say s1.name, would that be a compilable expression to write in my code? And also if I say s1.courses, so now you should put here either check or cross, right? And similarly, if I say rs dot let's say set dr, and then I'm going to put in this particular cell to say either check if it's a valid expression in the compile time, or put a cross if that's invalid, which means it wouldn't compile at the compile time. Okay, so that's the exercise I would like you to do. So download this PDF, print it out if necessary, and then fill in all the blanks, and then hopefully you identify some patterns for expectation. So I got just one little hint for you. So whenever we talk about expectation, think about what attributes, or to be more general, what features should be available on a particular type of objects. For example, for students, what should be available there, right? And also for resident students, what should be available there? Whatever that's available for resident students should be, number one, whatever that's inherited from its parents, or in general, ancestor. In this case, it would be the name and courses over here. Okay, and also whatever that's new, that's declared as new features like a premium rate and set premium rate, they should be also available to the students, resident student. So that'll be some quick hints to you, and then you can complete the matrix yourself. Okay, pause the video before you actually go on with the answer discussion. Okay, so hopefully you spend some time on the exercise. So let's now go over the answer. For those of you who actually consider your answer based on the dynamic types for the various objects, so that means you were on the wrong track, I can tell you. Okay, let's see what I mean by this. We'll go over more details later. So if you ever consider, for example, these types over here, the red dynamic types, so that means you were on the wrong track. Okay, in order to fill in this matrix over here to decide whether expression might compile at a compile time, all you need will be just the static types over here. Okay, so that's something I would like to emphasize over and over and over. Whenever we talk about expectation, so this is really to do with compile time. And whenever you talk about compile time, the only thing that matters will be the static type. So that's a very important principle you want to keep in mind. Maybe you have grasped this concept already in your previous OOP course. If you haven't, now is the time. Otherwise, you'll get very lost later in the lecture and also later in the design patterns. Okay, so now, since we only want to talk about whether an expression will compile or not, so all we need to look at will be static type. So now, in this case, would s1.name compile? So now let's think about expectation. Let's go over 1, 2, and 3, these three classes, and let's see. Let's say for the student class, let's just use green. So what would be the student's expectation? Everything that's actually declared in the students, and also whatever that's inherited from its parents. But now in this case, student is assumed to be the top of the hierarchy. So we only got name, courses, register, and tuition. So these 4 features are the expectation for the students at the compile time. Okay, let's now go over the expectation for resident students. So for resident students, what would be the expectation? Number one, whatever that's inherited from its parents will be also part of its expectation. So now implicitly, we also get, for example, name, and also courses, register, and also tuition. So these 4 are definitely the expectation for a resident student from whatever inherits from the parents. And also, what else? Also, all the new features that you declare in this particular class, premium rates, and also set premium rates. Of course, there's a slight complication over here. We actually got tuition being inherited, but we actually redefined that in this class. But that's okay. It remains to be the expectation. It's just about which version is going to be called at the runtime. But that one, runtime behavior, has nothing to do with expectation, nothing to do with it. We only talk about compile time. Okay, so let's now only keep the tuition here. So now symmetrically, what will be the expectation for non-resident students over here? So part number 1, everything that's actually inherited from its parents, which is common to the resident students. In this case, it would be, let me write it down, would be name, courses, also register, and also tuition. Okay, and then number 2, also all the new features you declare in this class, which will be discount rate and also set discount rate. And now notice one thing over here. Okay, let me just be very precise over here. Let me just erase this tuition here, and then I want to say the following. Let me use the yellow. So name, register, courses, and tuition. Name, register, courses, and tuition. Think about these two as the common expectation. Okay, so this set is just the same as this set over here. Think about these two sets as the common expectation. Common expectation inherited from their parents, which is the student class. It's very important to observe that. Outside the common expectation for resident students, they also got these two unique expectation, which is premium rate and this set premium rates. And also for non-resident students, they also got these two additional unique expectation. So you can see these two expectation is outside the expectation for resident students, and vice versa. These two expectation is also outside the expectation for non-resident students. Okay, having known this, let's now fill in the matrix, and then I'm gonna address one common confusion to get together with you before we move on. How do we fill in the matrix? So now that we know precisely the expectation, let's just try this, and then I'll try to speed up the answer filling. So what about for S1? You can see for S1 over here, its static type is simply just students. In that case, for student, we know precisely it should be name, courses, register, and tuition. And then for premium rate, for these premium rates, set premium rates, discount rate, and also set discount rate. So these will not be applicable to students because they only belong to, actually the subclasses over here. Okay, hopefully you agree. And then, so now for S2 and S3, it will be exactly the same. So now for S2 and S3, because their static type is simply just student, just the same as S1. So it will be the same. So I'm just gonna draw like this. So for S2 and S3, their static type, their expectation will just be the same, which means you can also call name, courses, register, and tuition, right? But for other unique expectation from either resident students or non-resident students, they are not available. Okay, so now I'll just use pink to say cross. Okay, so that means it's simply not available over there. So what about the next two? Let's say for the first one, let's say for RS, resident students. You can see for RS, its static type is simply of resident. I'm not even looking at the dynamic type, just the static type. For RS, you can see for RS, so now, first of all, the common expectation would just be name, courses, register, and also tuition. This one has no problem, right? I can tell you that even for NRS, it would just be the same. I can fill it in first, okay? NRS over here is simply of static type, non-resident student, but they got a common expectation that's inherited from the student class, right? Just a repetition here. So what about the rest? In the case of the resident, in the case of RS, what about resident student? What are the unique expectation? Well, premium rate and set premium rates. So that means we're going to do this. Premium rates and set premium rates will be okay. On the other hand, the discount rate and set discount rate, these are outside the expectation for resident students. And symmetrically, we can say the discount rates and set discount rates. So these are the valid expectation for the non-resident students, right? That's the NRS static type. And then the premium rates and also set premium rates. So these are the expectation for the resident students, which is outside the expectation of non-resident students, right? Hopefully you can see the pattern over here. So let me emphasize a few points before we depart from this example here. You can think about this part over here. Let me be precise. So this part over here, this part. Okay, let me just be very precise about the boundary over here. You can think about this part here is really the common expectation. Declare in the student class. So all the four: name, courses, register, and tuition. Okay, and then over here you can think about just put one of them. You can see over here, let's say this one here. You can think about this one here. So these are the unique expectation of resident students. And over here, let's put non-resident student. Let's use pink. This one over here. So this is the unique expectation. Unique expectation of non-resident students. Okay, so hopefully you can see the visual over here. Right, let me talk about one common confusion. Just take one example. Can we take a look at, let's say, this line over here? Let's say for S2. A common confusion goes like this. Let me say that over here. You can see that here S2 declared to be static type students. The way we answered the question was we don't even look at the dynamic type. However, some of you might be quite tempted to also look at the dynamic type. The way to visualize this line is by saying S2 is actually pointing to dynamically an object of type resident students, right? I'm going to use pink. Resident students. It's going to be resident students. And for resident students, most likely every resident student's objects is going to contain, the name, courses, register, etc. Specifically, it's going to have PR, the premium rates, and also the set premium rate as well, right? So now you can think about this premium rate over here is actually available on the objects. But why can we not to say S2 dot premium rate? You can see that corresponding cell is actually say you cannot do it. So this is a common confusion. So let me summarize, let me recap the common confusion first, and then I will tell you a brief answer. The common confusion goes like this. For S2, the static type is simply just students. And that is why when you say S2.PR, it's not going to compile because the PR is outside the expectation of the static type students. That's the answer. However, the common confusion goes like this. The dynamic type over here, this assignment is actually valid, as we will talk about later. Assuming that this assignment here is actually valid, so that means dynamically S2 is really pointing to this particular RS object which got PR as part of the object fields. In that case, why can we not call S2.PR? Okay, that's a common confusion. Okay, my answer to you is whenever you want to talk about compilation property, whether a particular expression S2.PR, whether that should compile or not, you never ever look at the dynamic type like this. You never ever. All you're going to look at will be just S2 is static type student. So as easy as is the PR is simply not available. Okay, so that's my very first emphasis to you about whenever you want to discuss about compilation, always look at the static type and for the expectation. Okay. All right, let's go back to the slides. And then, so that's exactly the matrix that we talk about. Okay, you can review it. Okay, hopefully that matches the answer from you. So this may be something you learned already from the previous OOP, but without knowing too much about why exactly that's the case. But we'll explain that.